welcome to this module, and this module is continuation with the last module, in which we have seen what are the basic building blocks for signal conditioning circuits, right. So, in the last module what we have seen is how we can use Wheatstone bridge for resistive sensors with constant voltage source and constant current source, and what are different type of resistive sensors that we can use, and what kind of elements we can vary. Either we can have a one variable resistor, or we can have two in two different ways, or we can have all four resistor in a varying condition, right, and we have seen the advantages of both. So, let us see a very important amplifier, and that is used for a lot of signal conditioning circuit, and that is your instrumentation amplifier. Now, the instrument amplifier had several advantages. Some of the important characteristics are: it has a very high gain accuracy, extremely high input impedance, low output impedance, low DC offset voltage. When there is no signal input, output should be 0, right, and then high gain stability with low temperature coefficient, as well as it has extremely high CMRR. Now, you know what is CMRR, right? We have seen CMRR is given by ratio of CMRR is common mode rejection ratio, is a AD differential gain by common mode gain, right, mode of AD by ACM. The we want ACM to be extremely low, we want differential gain to be extremely high, right, so that we can faithfully replicate the signal and we can have the gain only from the difference of the signal. Thus, CMRR should be extremely high. So, this particular instrument amplifier has the advantage that it has a very high CMRR. Okay. Now, you can also understand that what is advantage, so that it can reject the common signals to both the terminals. So, this instrument amplifier is the best option for signal conditioning for low value sensor responses. It is 2-stage configuration with 3 operational amplifier, you can see here, right, 1, 2 and 3. There are 3 operational amplifiers that are used, right, and then you can see further that this amplifier as well as this amplifier are nothing but the inverting buffers, right, and non-inverting buffers, because the signals are applying to the non-inverting terminal, as you can see here and in this particular case, while the second stage is an amplifier which has a variable gain, right. This is a amplifier with a variable gain, is nothing but a differential amplifier, right. Now, gain in multiple stages, that is high gain, so you can amplify small signals, that is the advantage. Second is that as a bonus you can put some low pass and high pass filters if you want to. The differential amplifier, which is this amplifier here, it rejects common mode interference, so you can reject the noise. Further, the differential amplifier with a very high input impedance, so you can connect to the sensors, right. Now, we have seen the if you know the little bit about operation amplifier and the loading effect, then you will understand and appreciate why we are using a very high input impedance amplifier sensor in the circuits. So, in continuing this particular amplifier, if we see further, the instrument amplifier is a closed loop device like the differential amplifier, but with a carefully set gain and additional input buffer stages, right. If you see this one, it is what differential amplifier. What is that? What is the difference here? That you have the buffer at the input, and you also have the carefully set gain. Now, the gain can be precisely set by a single internal or external resistor, right, and another thing is that the addition of input buffer stages makes it easy to match the amplifier with the preceding stages. If you want to match this amplifier, if you have the voltage follower here and here, then it is easy to connect the preceding stages. This is before the this particular instrument amplifier circuit. So, you can easily connect sensors to it, you can easily connect Wheatstone bridge circuits to it, and so on and so forth. The further, this allows instrument amplifier to be optimized for its role as a signal conditioner of a low level, that is often as a DC signals in large amount of noise. The high common mode rejection makes this amplifier very useful in recovering small signals, because most of the sensors that you use, the output is generally extremely small, and the small signals you need to catch it, and you have to reject the common mode signals. So, when you want to catch a small signals and you want to amplify it further, so if the sensor is not is sensitive, but it is not that sensitive that it will show enough change in resistance. If it is a resistive sensor, then instrument amplifier can play a very important role, because it can catch a small signal and amplify it further. And additional advantage of instrument amplifier over differential amplifier is that because there are two buffers as the input, it can easily match with the preceding stage. So, that things are comes as a handy when you are actually designing a signal conditioning circuit. Further, if you can see the voltage, then voltage is given by V out equals to R 4 by R 3 to 1 plus 2 R 2 by R 1, and the difference of the voltage V 2 and V 1. This is difference of signal at the input stages. So, if I want to use now, let us take a few examples. Let us have first example as the sensor based electronic system for real world. That means, if you have a plant, right, and you want to control the it's a signal acquisition system as well as the feedback system. You can see that the if it is there is a sensor or transducer, right, and what exactly this does, it converts it to a discrete signal, and the discrete signal can be given back to a proceed analog signal. So, like a feedback system, right. So, suppose you want to measure the temperature, or you want to measure the let us say the motor parameters. For example, if the motor is having too much vibration, it is dying. So, that vibration can be used as a important parameter to understand the lifetime of a motor. The temperature of the motor can also be used as a lifetime for understanding the lifetime of the motor. For example, if the temperature increases too much, then you can say that there is fault in the system. Thus, if you want to have a feedback system in the real time, then you can use this kind of signal acquisition system with a output module. So, let us see that what kind of sensor. For example, if we take the temperature as one of the parameter, right, then you have a thermistor, and the so you can say here is a sensor or transducer as a first block. Then what is the signal? It is analog signal. So, you need to have the filtering as anti-aliasing filter at the second block. Then you have a band limiter analog signal. Now, you can use sample and hold circuit to convert the signal, and then you can sample this signal into the ADC, and then finally, with the discrete signal you can run a controller, microcontroller. Now, depending on what is the temperature that you want to maintain, right, you can switch off the plant, or you can change the that particular parameter by giving a feedback. So, now the feedback is digitally output. These digital outputs are converted to analog domain. There is a smoothing filter, and then you have a driver circuit, so that to proceed the analog signal. So, now what you are doing is in a way you are converting the analog signal to digital signal and feeding it to controller, and then taking the digital signal from the controller and feeding it back to the plant. So, converting back to the analog. So, this is how the electronic module works when you take the signal acquisition and the output module. Now, let us take a very interesting example, which is your ECG signal to calculate bits per minute. Okay. Now, why we are learning ECG? Now, we are learning ECG because we want to understand that functioning of the heart, right. So, the point is, how can we design a signal conditioning circuit for measuring this ECG signal. One of course is the bits per minute, what is the heart rate, right. So, for doing that, what we have to learn? We have to learn instrument amplifier, we have to learn high pass filter, low pass filter, we have to learn the notch filter, we have to learn the half wave rectifier, we have to understand how it is a triggering unit, and then bringing all together we can understand how the signal conditioning circuit for a ECG would work. Okay. So, let us see each circuit in detail, and then we will talk about the how to bring all the circuit together to form the entire signal conditioning circuit. Let us see how to develop an electronic module for designing or for measuring the ECG signal. Now, ECG we know is used for monitoring the health of the heart. So, how whether heart is working properly or not. So, ECG is one of the extremely useful signal to understand the functioning of heart. Now, when we are talking about functioning of heart, we are also talking about the how many beats per minute the heart is pumping, right. So, to understand or to develop such a module, we need to understand how can we now use what we have learned in the previous module, different amplifiers, different filters, right, half wave rectifier and a triggering circuit, so as to integrate all those components together and form a signal conditioning circuit for the ECG. So, let us see the first point, and that is the how to design the this particular system. So, the first thing, let us understand the introduction, and the introduction about ECG is analyzing electrocardiogram, which is also called ECG, is not only important to understand the functioning of the heart, but also to understand the abnormalities, and the conditioning of the heart is evaluated using ECG signal. Now, it is one of the simplest, fastest, easiest, cost effective method to evaluate the functioning of the heart, and thus ECG monitoring has become a primary test in today's modern hospitals. The electrical activity is related to the impulses that travel to the heart and that determines the heart rate and the rhythm, right. So, this is a important point for us, because we want to understand how can we measure this electrical activity, and this electrical impulses causes the heart to contract and relax are detected by nothing but the ECG machine and are transformed into form of the waves that can be displayed on a graph or a monitor, right. So, several heart problems such as premature contractions, heart block and fibrillations are diagnosed using ECG signal. We will understand what exactly fibrillation means, what is the difference between in a different kind of fibrillation. We will in particular will focus on atrial fibrillation and sensors that can help to make the catheter smarter for performing the ablation. So, we will talk about this particular heart disease at the end of this module, but first let us understand that how can we design this signal conditioning circuit. So, the aim of this particular experiment, you can say, because why I am saying experiment, because we will also see in reality how can we design electronic conditioning system which is consisting of acquisition, conditioning and processing in a real time. Okay. So, we will see as a part of the experiment. So, let us see the aim is to extract and process the ECG signal from the body and to compute BPM. Several modules are to be used. In this experiment, we will divide the complete system into several subsystems, compute the functionality of each system. So, the following are the subsystems. The first one is the acquisition of ECG signals using non-invasive method, right. This is the first one that we will see. The second system that we will see is how to design a ECG amplifier circuit. The third system that we will look at is the designing of QRS and half wave rectifier for noise filtering, and then we will go for how to understand how to design a comparator and threshold circuit for peak detection, followed by QRS pulse detector, followed by triggering circuit for BPM measurement, and then the equipment that we require to understand these ECG signals in the laboratory would be a digital oscilloscope, function generator, we require ECG electrodes and operation amplifiers as well as connecting wires, right. So, let us see the first one, and the first one would be acquisition of ECG signals and design of the ECG amplifier circuit. So, here you can see that an ECG signal is a very weak signal with a range of just 1 millivolt in amplitude with a frequency range of 0.05 to 120 hertz, right. So, this is a very important point for us, because we have to amplify this signal which is extremely low. As the signal amplitude is very small, to process the signal it must be amplified with a high gain of about 1000, right. The typical characteristics of the op amp should be high input impedance, low output impedance, high CMRR. We know that these are kind of ideal characteristics, that infinite input impedance, zero output impedance and extremely high infinite CMRR, but the practical op amps would have high input impedance, low output impedance and high CMRR. So, the typical circuit for the amplification of ECG signals uses instrument amplifier, which is shown in figure 2. This is the typical circuit. Okay. We will see in detail how it is done. For now, let us understand the block diagram of the QRS detection. So, for the QRS detection, we have to understand that we have the ECG amplifier, which will be followed by pre-processing and then half wave rectifier, peak detector and finally the trigger unit, right. So, these are the steps in the case of the QRS detection. Okay. Then we will move further, and further is that we have to design a QRS detector circuit. So, to compute bits per minute, QRS complexes are used. The frequency of QRS is about 17 hertz. The detection of QRS is represented using the block diagram, which we have just discussed. So, let us now see how can we develop ECG amplifier for the QRS signals as well as the BPM. So, the first one is you have to connect the V1 and V2, which is the inputs to the instrument amplifier to the signal high. This is the common node or common mode operation, and we have to calculate its common mode gain. The second process is we have to connect V1 to the input signal high and V2 to the signal low. So that this is a differential mode operation, and we calculate the differential mode gain. Finally, we will connect all 3 electrodes to the body as shown here, RA, LA and RL to the and we can see that RL is connected to the ground through 10 kilo ohm resistor, and then connect these electrodes to amplifier inputs and observe the amplifier output at the oscilloscope. Now, whatever I am saying, it will become little bit difficult for you to understand directly, but when we go for the experiment, then we will understand in detail how this is done in reality. Okay. So, the pre-processing, which is a important part, how we are performing that experiments or how we are developing the system for the pre-processing. The amplifier ECG signal is processed through a filter to remove the noise or unwanted signal. Pre-processing of ECG signals helps to remove contaminants. Alright. So, we have to pre-process the signal before the next stage. So, and then ECG contaminants. So, what actually contaminants in ECG signals are? The contaminants in ECG signals are that we have electrode pop or contact noise. We also have baseline wandering. We have EMG noise, right, which is also called electromyograph, and then we have patient electrode motion artifacts, right, because if you connect the electrodes, if the patient is moving, then there is a motion artifact. We have to take care of that, right. We have to take out the EMG. EMG comes from the muscles, right, the signal coming from the muscles. If I am moving my muscles, then there is a signal that is generated from the muscles, which can be measured with the help of electromyograph. Okay. And then we have power line interference, that is a extra thing that will come into effect. We have contact noise, we have electrode pop. So, all these things will contribute in the contaminants for measuring during the measurement of the ECG signal, right. So, now, for our country, the power line noise comes is a narrow band noise around 50 hertz and with a bandwidth of less than 1 hertz. So, we can use a notch filter at a frequency of 50 hertz, right. Now, you have seen different filters, and in this the notch filter, if you can design for 50 hertz, you know, right, what is notch filter? It is a band reject filter. Now, if it is just single frequency, it looks like a notch, that is why we say notch filter. So, if you can design a notch filter for 50 hertz frequency, then the power line interference will be taken care of. So, let us see here what I was saying is that there are several contaminants. We have just seen 1, 2, 3, 4 and 5, and then the power lines interference in narrow band noise around 50 hertz, we have talked about it. Notch filter we can develop a center of 50 hertz. However, these signals are odd multiple and can be filtered using a low pass filter with a cutoff frequency of about 100 hertz, right. Since these are the odd multiple, we can use the cutoff frequency of 100 hertz, and since this is below 100 hertz, we can use a low pass filter. The motion artifacts, which are the another contaminants, and the range of less than 1 hertz, hence high pass filter with a cutoff frequency of 1 hertz can be designed to filter out the noise due to motion artifacts. So, what we require? We require a low pass filter with cutoff frequency of 100 hertz, we require high pass filter with a cutoff frequency of 1 hertz, and finally, we require a notch filter with a center frequency of 50 hertz. So, these are the requirements for pre-processing. Now, let us see how can we design each of these filters. Okay. We start with the low pass filter. So, you can see here in the circuit, right, the circuit is of low pass filter, and if we keep a value of R 1 and R 2 as 670 kilo ohm and capacitors value as 2.2 nanofarad, and then we have a gain of 1 and our frequency will be 1 by 2 pi R c. So, f c equals to 1 by 2 pi R c, and that will give us close to 108 hertz. This is our low pass filter design. For the experimental procedure, what we can do? We can apply a sinusoidal signal of 1 volts amplitude generated by signal generator at 1 hertz into the integrator and observe the output, input and output on the oscilloscope. We can also calculate the gain. Second one is that with a frequency of 1 hertz, increase the signal frequency time step of 20 hertz up to 200 hertz and record the output of each frequency. This is actually the experiment procedure. Finally, we can also go for observing the signal generator frequency, for which the output is 0.707 times lower than the input signal, which is your minus 3 dB point. And finally, you can have the we have to verify the operation of a low pass filter where the input frequency greater than the cutoff frequency should not pass, right. So, this is how you should perform the experiment. Like I said, we will perform the experiment for the ECG in detail. Now, let us understand the second part, which is your high pass filter design. Now, in the high pass filter design, what we are working on? We are working on designing a high pass filter, right, which you can see here, and here you, if we have resistance value of R 1 R 2 equals to 1 kilo ohm and R 3 R 4 equals to 1.5 kilo ohm, where C 1 equals to 100 microfarad and C 2 also equals to 100 microfarad, then we know the F c, which is the cutoff frequency value, will be nothing but 1 by 2 pi under root of R 1 R 2 C 1 C 2. Since R 1 equals to R 2 and C 1 equals to C 2, you can have, or you can, in this case is like R 3 R 4 C 1 C 2. So, if you have these values, then what will be the F c? F c would be nothing but 1 by 2 pi under root of R square C square, which is nothing but 1 by 2 pi R c, right. So, this is what we are using here, and that is why it is 1 by 2 pi R c, and what we get is close to 1 hertz. Your gain is nothing but 1 plus R 2 by R 1. Okay. So, this is the formula. For experimental procedure, we will apply the input voltage, which is sine wave of 1 volt amplitude and generated by at 200 hertz into the differentiator, and observe the input and the output at the oscilloscope, and we calculate the gain. Second one is, starting with a frequency of 200 hertz, we decrease the signal frequency in step of 20 hertz to near DC and record output at each frequency. Finally, we will observe the signal generator for the frequency for which the output is 0.707 times, or you can say minus 3 dB point, or the low corner frequency, and we will verify the operation of a high pass filter, not low pass filter, where the input frequency lower than the cutoff frequency should not pass. Now, how can you design notch filter? Notch filter is very easy to design. We have seen in the earlier modules. Here what we have is FO equals to 1 by 2 pi R 1 into C 1, which is 1 by 2 pi R c. We substitute the values which are already given here, and you can design the notch filter. Right now, here if you want to perform the experiment, what you have to do is to apply the 1 volt amplitude generated by signal generator at 50 hertz into the filter, and observe the input and output voltages on the oscilloscope. Then we can change the frequency from 30 hertz to 80 hertz in a step of 10 hertz and record the output at each frequency. What we want, we are that 50 hertz should not pass through the filter, and remaining frequency can pass through. We can observe the signal generator frequency, for which the output is again 0.707 times lower than the input signal, or you can say it is a minus 3 dB point, and finally we can verify the operation of a notch filter. This is how the filters are designed. So, what if you see, go back, what we have to do? We have to design a low pass filter, high pass filter, and a notch filter. So, that is what we have done here. Then let us understand the next stage. So, we are now understanding the half wave rectifier. Now, in the case of a half wave rectifier, the filtered ECG signal is rectified using a half wave rectifier to remove the negative signals, right. We do not require negative signals, as our intention is only to find out the positive peak the negative peak will be rectified using a half wave rectifier. So, what is experimental procedure? Experimental procedure is apply a sine wave input signal of 1 volt in the input V in at 100 hertz generated by signal generator at the non inverting terminal, which is right over here. Then we have to observe both input voltage and the output voltage on the oscilloscope. Next one would be we will verify the operation of a half rectifier. Half rectifier very easy to design, which is right over here. So, it is very extremely simple design, right. Now, let us go for the next one. The next one is nothing but a peak detector circuit. So, for peak detector circuit, what is a circuit, how circuit will look like? Circuit will look like the one shown here, and how it is going to help us, because it is used to store the peak of the filter signal using the capacitor, right. The fraction of the peak voltage is used as a threshold voltage is compared with the filtered and rectified ECG signal using the comparator, right. This is your this one. Once the QRS pulse is detected, when the threshold voltage is exceeded, the capacitor recharges to a new threshold value. So, this is the threshold voltage. If it exceeds the earlier one, the capacitor will recharge to a new value, right, after every pulse, and the new threshold determined from the history of signal is generated after every pulse. The output voltage you can measure right across this particular circuit. And if you want to verify the circuit using experiments, then what you have to do, you have to apply a DC input signal of 1 volt at V in, observe input and output voltage on the oscilloscope, and you have to verify the operation of a half wave rectifier. Now, if we see, so you can also, so in case of signal, you can also apply the sine wave and look at the operation. It is not just like every time you have to go for DC, you can also increase the frequency and you can see what happens at the input and what happens at the output for the same for the same circuit, but at the different for the different signal. Finally, if we understand trigger unit, then it becomes very important, because trigger unit is nothing but a pulse generated for every QRS complex that we know, and is detected using the comparator and triggers the LED, which is right over here. So, every time the QRS complex is detected, we there is a comparator here, and whenever there is a high, the LED will glow. When there is a low, the LED will not glow, because it is a comparator circuit. You know the functioning of a comparator. If it is non-inverting signal is higher than the inverting signal, the comparator output will be higher. If the inverting signal is higher than non-inverting signal, then the output will be lower, and based on that the LED will glow or it will not glow, or you can drive or we cannot drive the LED depending on the signal at the output. For the experimental procedure, we can apply a input DC, a pulse input DC, a signal of 5 volts at the input voltage V in. You can observe the input and output voltage on the oscilloscope, and finally we can verify the operation of circuit as a monostable multivibrator, right. So, what you observe here? You observe a very interesting application. What we have just understood is there is an instrument amplifier, there are filters, and then there is a comparator, and there is a triggering circuit. So, when we connect these leads to the instrument amplifier, right, then what will happen? The instrument amplifier will pick up the signal, and we will because of its high CMRR, the common mode signals are rejected, and the differential signal is amplified and further fed to the low pass filter, right. Now, we know for low pass filter we have designed a filter which can filter out anything above 100 hertz, and then we have a high pass filter that is for anything for the 1 hertz frequency. Then we have a notch filter that is for the 50 hertz frequency. Then we have a half wave rectifier, because we are interested only in the positive signals of the QRS, and then we have a peak detector where for every QRS signals it will detect a peak, and finally we have a LED. So, that LED will help us to understand how many bits per minute these QRS signals are generating, and that will help us to understand the count the number of bits, right. So, now what do you guys see? You guys see that integrating all the circuits together will form a signal conditioning unit, right. This is how the ECG would work, right. In the next module we will see two different aspects. One is how can we design a force sensing unit, right, and what kind of signal conditioning circuit we have to use to understand the force from the catheter. Now we will see in the next module, but for this module just understand that if you know the each block in detail, you can integrate those blocks and you can use for practical applications such as ECG, right. So, till then I will see you in the next class, and you just look at the look at this particular video. If you have any questions, feel free to ask us in the forum, right. So, take care, and I will see you in the next class. Bye.